let's look at some examples of using integrals to find areas. So here's a typical area problem. So let's find the area of the region here between x squared and y equals x squared and y equals x. Right, keep in mind that we had this formula, integral from a to b of f of x minus g of x. And f has to be the one on top for this to work, right, dx. So f has to be the one on top. Okay, now if you look at this region, I mean, it kind of looks like the right-hand end of this region is at 1, but the way this problem is stated, it's not actually clear that it is at 1. So what we should do is figure out what exactly the extent of this region along the x-axis actually is. And this is because we need to use the left and right end of this region to write our bounds. So in order to write this integral, we have to know the bounds. And the bounds are where these curves intersect. So let's figure out where these curves intersect. So we suspect that it's at 0 and at 1, but let's just double check. So the bottom one, the parabola, is x squared. The top one is x. We want to know where are those equals, so we're going to set them equal to each other. And then we can manipulate this algebraically to solve this equation. So move the x to the left. X squared minus x equals 0, and then factor x times x minus 1 equals 0. And yes, sure enough, we get x equals 0 and x equals 1. So these two graphs intersect at x equals 0 and x equals 1. So that means when we do our integral, we're going to go from 0 to 1. And notice we're always going from the smaller x value to the bigger x value because we want our area to come out to be positive because it's an absolute area, not a signed area. So we have to go in the we have to integrate in the positive x direction. Okay, so now let's finish writing out our area integral. So it's the top function minus the bottom function. And the top function is just a line, that's y equals x. And then the bottom one is the parabola, so that's x squared. And we're integrating dx. Now that we have this integral written down, we can actually evaluate it just using the whatever tricks we have in our toolbox. And of course, for this example, the main trick is going to be using the fundamental theorem of calculus. But often, writing down the integral that you want is the hard part. So, don't rush through actually writing the integral. Be sure that you get all of the pieces for the integral set up correctly. Once you have it written down, then you can, temporarily forget where this integral came from and just concentrate on evaluating it. So to evaluate this integral, we can just write down an antiderivative for this function, for this integrand. So that's going to give us 1/2 x squared minus 1/3 x cubed. And we're going to evaluate from 0 to 1. So plugging in 1, we get 1/2 times 1 minus 1/3 times 1 minus, and then plug in 0. We get 0 minus 0 for this one. So 1/2 minus 1/3, that is a sixth, right? It's 3/6 minus 2/6, that's 1/6. So the area of that little curved wedge is exactly 1/6 of a square unit of area. All right, let's look at another example. Okay, so here we're going to find this pictured area, that's cross-hatched here, between the parabola and the line, and here are the equations for the parabola and the line. And we're going to go from x equals -2 to x equals 1. So when we came up with this formula for area, integral from a to b of f of x minus g of x, we said that f of x has to be on top for this formula to work. But if you look at this, setup that we have, which function is on top actually switches partway through the integral, right? At first the line is on top, but then when you get far enough to the right, the parabola is on top. So we can't use this formula directly, right? If we did, then when we get to this right hand, I guess it's when we're at the left hand part of this region where the line is on top, right? We can't use g of x. We can't put g of x second because g of x is on top for this part. But we can't put f of x second because f of x is on top for the right-hand part of the integral. So we need some way of modifying this formula so that we don't accidentally make it negative some of the time. Well, if we want it to always count as positive, we just need to throw absolute values in here, like this. So this integral will always give us the absolute area, so the unsigned absolute area, if we have a region that's bounded up above and below by a graph, and on the left and the right by x values. So we can just throw this all our information into this formula. Of course, with the absolute values, it doesn't actually matter which function you put first, f of x or g of x, so I guess we might as well put f of x first. So we're integrating from a to b. Sorry, a is -2, b is 1. The absolute value of f of x, which is minus x squared plus x plus 1, minus g of x, which is x, dx. And then to evaluate this integral, I guess we should simplify the stuff inside the absolute values, right? These x's cancel. So we're looking for the integral from -2 to 1 of the absolute value of 1 minus x squared dx. Okay, well, if you think back to definite integrals we've done where there's an absolute value in our integral, we have to split this integral up where 1 minus x squared crosses 0, right? Because for some x values, this absolute value will leave 1 minus x squared alone, and for other x values, the absolute value will put an extra minus sign on the whole thing. So we need to separate the two cases. So just to have a picture in our mind, so let's graph 1 minus x squared. It looks like this. And it crosses the x-axis at -1 and +1. So right, our integral is going from -2 up to +1. So it looks like we need to split up this integral at -1. So we'll integrate from -2 to -1, absolute value of 1 minus x squared dx, plus the integral from -1 to 1 of absolute value of 1 minus x squared. Okay. Now for the integral on the left, integral from -2 to -1, for these x values, for x values from -2 to -1, 1 minus x squared is negative for these x values, and so the absolute value will put an extra minus sign on there, like this, minus 1 minus x squared dx. Okay, plus the integral from -1 to 1. For these x values from -1 to 1, 1 minus x squared is positive, and so the absolute value just leaves it alone, like this. And now that we've dealt with the absolute values, there aren't any absolute values in our integrands anymore, we can go ahead and evaluate these integrals in the usual way, just using the fundamental theorem of calculus. So let's see, first thing I want to do is move this minus sign outside the integral, just because that's how I like it. And then integral of 1 minus x squared is x minus 1/3 x cubed. And we're going from -2 to 1, sorry, -2 to -1, plus, and then integral of 1 minus x squared, again, that's x minus 1/3 x cubed. But this time we're going from -1 to 1. All right, and now we just need to barrel through all of this arithmetic. So let's plug in -1. So -1 minus 1/3 times -1 cubed. Right, that's going to cancel this minus sign in the middle. Minus, and then we need to plug in -2. So -2 minus 1/3 times -2 cubed. Okay, so that's the first integral. Plus, and then for the second integral, way up here on the right, we need to plug in 1. So 1 minus 1/3 times 1 cubed, but that's 1. minus, and then plug in -1. So -1 minus 1/3 times -1 cubed. Okay, so negative, let's see, -1, this is plus 1/3, so 2/3 minus, then in here we have 2, let's see, this is -2 plus 8/3, so that's going to give us 2/3, positive 2/3. Okay, so looks like these cancel. Okay. Plus the second part, so 1 minus 1/3 is 2/3 minus, and then in parentheses here we have -1 plus 1/3, so minus 2/3 again. Okay, so this together is 4/3. Right, so this integral, this region here, this piece and this piece, has area 2/3, or I'm sorry, 4/3.